So, very good morning. So, now we are into module 6 of fluid properties. In the last module, we discussed some application problems on viscosity, and in this module we will move into the subsequent fluid properties. We will start with vapor pressure. Now, if you take any liquid, so this vapor pressure is a property of a liquid or any liquid for that matter. The tendency of any liquid is to vaporize or evaporate. So, any liquid will tend to evaporate or vaporize. That is, evaporation is a process wherein the liquid molecules are converted into gaseous molecules. So, from liquid state it is converted to gaseous state. Now, we know that all liquids have got a free surface. So, let us consider a vessel containing a liquid. Let the liquid be water. Now, this is open and the free surface is marked like this. Now, the liquid molecules, they exhibit mobility. They always exhibit mobility. They move from one point to another, and the molecules which come near the surface, which come to the surface, so they escape through the free surface. Molecules of liquid escape through the free surface as vapor, in the vapor form. Now, because of the continuous escaping of molecules through the free surface of liquid, the molecules which get ejected out of the container, they get accumulated in the space. Say for example, you consider the vessel is closed. Suppose the vessel is closed. Now, what happens? Because of mobility, the molecules which come to the free surface, they have the freedom to escape to the overlying free space, the atmospheric space we will call, and these vapor molecules will exert a pressure on the free surface, So, the pressure exerted by the accumulated liquid vapor on the liquid surface, that is on the free surface, that is called partial pressure. So, why it is called a partial pressure? So, let me summarize. The tendency of any liquid is to evaporate or vaporize, that is, the liquid changes to the gaseous state, and any liquid which is contained in a vessel will have a free surface, and the continuous escaping of molecules through the free surface will get accumulated. Suppose if you consider a closed container like this, will get accumulated in the free space over the free surface, and this vapor which gets accumulated, because it cannot escape, it has to occupy only this region. As there is a continuous escaping of molecules, the vapor molecules will increase with time, and this will exert a pressure on the free surface, and the pressure exerted by such vapor on the free surface of liquid is called a partial pressure. So, why it is called a partial pressure? So, why the pressure exerted by the ejected vapor on the free surface of liquid is called a partial pressure? Now, what is that which is prevailing in this free space? We have atmosphere. Now, atmosphere. So, what are the constituents of atmosphere? The constituents of atmosphere, the major constituents are nitrogen and then oxygen. So, these two put together, they constitute more than 90% of the total constituents of atmosphere. So, nitrogen will exert a pressure, oxygen will exert a pressure on the free surface, and the vapor molecules which eject through the free surface of liquid will also exert a pressure. So, atmospheric pressure means it is the sum of the pressures exerted by the various constituents of the atmosphere. The major constituents are nitrogen and oxygen. Nitrogen more than 70%, oxygen and then more than 20%. Now, these molecules of vapor ejected through the free surface of liquid become part of the atmosphere. So, they become part of the atmosphere which is overlying the free surface of the liquid in the vessel. So, the magnitude of atmospheric pressure is the sum of the pressures exerted individually by the different constituents of the atmosphere, including the ejected vapor molecules. Therefore, the pressure exerted by ejected vapor molecules is part of the atmospheric pressure, and that is why it is called partial pressure. It is called partial pressure. Now, let us discuss on the factors influencing vapor pressure. What is the influence of temperature on vapor pressure? Now, what happens when the temperature of liquid rises? We have discussed in viscosity that when the temperature of a liquid rises, the molecular mobility increases, the molecular activity increases. That means the molecules have more freedom to move from one place to another place within the liquid. And because of increased molecular activity, more molecules get the opportunity to escape through the free liquid surface as vapor. So, when you increase the temperature of the liquid, the molecular mobility increases, and because of increased molecular activity, more molecules have the tendency to escape through the free surface of the liquid, and therefore, with increase in temperature, as more and more vapor molecules get accumulated over the free surface of liquid, there is an increase in vapor pressure. So, with increase in temperature, the vapor pressure also increases. So, with increase in temperature of the liquid, the vapor pressure also increases. Now, here we make a statement that a liquid may start boiling even at ordinary temperature. A liquid may start boiling even at ordinary temperature. How? How to justify this statement? Now, let us take the classical liquid, that is water. Water has a boiling point of 100 degree centigrade. Boiling point of water is 100 degree centigrade. Boiling point of water is 100 degree centigrade. Now, may start boiling even at ordinary temperature. Ordinary temperature means, say, the room temperature or the ambient air temperature. So, how it is possible? Now, see, we have to consider two things. One is what is the atmospheric pressure, the overlying atmospheric pressure, and what is the vapor pressure of the liquid. Now, when the external absolute pressure that is imposed on the free surface, that is the atmospheric pressure, is reduced by some means. See, it is a hypothetical case, just for the sake of discussion. When the external absolute pressure imposed on the free surface of liquid, that is the atmospheric pressure, is reduced by some means, to what an extent? To such an extent that it becomes equal to or less than the vapor pressure of liquid. So, vapor pressure is a function of the temperature. So, what is the temperature of the liquid? What is the ambient air temperature? And what is the atmospheric pressure corresponding to the ambient air temperature? And what is the vapor pressure corresponding to the temperature of the liquid? So, when the external absolute pressure, that is the atmospheric pressure, which is acting on the free surface of liquid, is reduced by some means such that it becomes equal to or less than the vapor pressure of the liquid, the boiling of liquid starts. The boiling starts. So, normally the boiling point of water is taken as 100 degrees Celsius. So, irrespective of the temperatures here. So, irrespective of the temperature. So, a liquid may start boiling even at ordinary temperature. So, when it is, when you can decrease or reduce the external absolute pressure, which is the atmospheric pressure, by some means, such that it becomes equal to the vapor pressure of the liquid, then the boiling of liquid starts irrespective of the temperature. Now let us discuss what is the influence of pressure. Suppose if at any point in a flow system the pressure of the liquid approaches vapor pressure. Suppose, say for example, you take flow through a pipe. Suppose if the pressure at any point in the flow through the pipe system approaches vapor pressure, then vaporization of liquid starts, resulting in pockets of dissolved gases and vapors, which is not advisable, particularly in the case of flow through pipes. Now another question, why mercury is chosen to be the liquid for use in the barometer measuring atmospheric pressure? So barometer is a device used for measuring atmospheric pressure. So why we use mercury as a manometric liquid or the barometric liquid? The reason is that mercury is the liquid which has a very low vapor pressure. So very low vapor pressure, because the tendency to evaporate or vaporize is very less in the case of mercury. So it has a very low vapor pressure, therefore it becomes an excellent fluid for accurate measurement of the atmospheric pressure. That is why it is used in the barometer. Okay. Now state an example for a liquid with a very high vapor pressure. So benzene is one example for a liquid wherein it has got a very high vapor pressure. So the tendency to evaporate or vaporize is very high in case of benzene. The tendency to vaporize or evaporate in the case of mercury is very less, and that is why it is used in barometers for accurate measurement of atmospheric pressure. So now we move into the next property, that is compressibility. So compressibility, so again I recollect, so fluids, it can be a liquid or it can be a gas. Liquids and gases are put together called fluids. Liquids are generally incompressible, they cannot be compressed under ordinary circumstances. Under special circumstances a liquid can be compressed. But gases are highly compressible, and when you release the compressive force they are free to expand to any extent. So fluids, that is here you should read it as gases, can be compressed by the application of external force. Even liquids can be done under special circumstances. So ordinarily in most of the engineering problems we come across, liquids are generally treated as incompressible, they are incompressible, whereas gases are highly compressible. So let us say the fluids can be compressed by the application of external force. Now when you remove the external force which is applied on the fluid, the compressed volumes of fluids expand. The fluids, that is the compression is released, the volume is expanding to the original volumes. So the fluids also possess elastic characteristics like elastic solids. So when you release the force, it will expand. The volume expands to the original volume. So let us now define compressibility of a fluid. Now compressibility, it is nothing but the reciprocal of the bulk modulus of elasticity of the fluid. Compressibility is nothing but the reciprocal of the bulk modulus of elasticity of the fluid. So how is bulk modulus defined? So bulk modulus is given the notation capital K. It is stress divided by strain. So stress is nothing but the increase in pressure due to compression, or the change in pressure we call. It can be either the compressed gas, you can release the compression, or you can add compression by increasing the pressure. So change in pressure, and strain is nothing but the ratio between the change in volume and the original volume of the fluid. So what is the change in volume due to change in pressure, say an increase in pressure? What is the reduction in volume? And what is the original volume? So dV over V. So dP is the change in pressure, say, or the increase in pressure. dV is the change in volume or the decrease in volume, and capital V is the original volume. Now let us consider a fluid. Let me present it by, schematically, just for the sake of discussion. Say this is the original volume, say, for example. The hatched portion is the original volume. So the pressure that is acting here be P. Now I am increasing the pressure which is acting on the gas by dP. Let the new pressure be P plus dP. Now what happens? This is the original volume. Now the volume gets reduced. Say now this is the reduction in volume, say dV. Now the new volume is V1. So V1 is less than V, or V1 is equal to V minus dV. Now I am increasing the pressure by another increment which is also whose magnitude is equal to dP. So the pressure becomes P plus 2 dP. So here it is, this is P plus dP. Now P plus 2 dP. So what happens now? The volume is further decreased, say to V2. So I will use a new color. Say this is this line corresponds to the original volume. This dotted line corresponds to V1. Now the dotted line that is below the first dotted line, let us say the volume is now V2. So V2. So V2 is less than V1. Now what will be V2 in terms of V? So will it be V2 minus 2 dV? Oh, this is wrong. Why? See, initially the pressure was P, the original volume was V. When the pressure was increased to P plus dP, that is P plus dP, when the pressure was increased by dP, increment pressure dP, that is P plus dP, the reduction in volume is dV, that is the volume becomes V minus dV, okay, V minus dV, that is V1. Now when you increase the pressure by another increment dP, that is when the total pressure becomes P plus 2 dP, the volume is further decreased, not by the same quantity dV. It is decreased, the volume is decreased by not by the same quantity dV, but by a quantity which is less than dV, Why? Because when you apply the pressure, what happens? Because of increased molecular activity, say it is a gas, the molecules come closer together. Then when you apply another, when you increase the pressure further, as the molecules have already become close together, they will offer resistance. Therefore, further closing down of molecules will be decreased, and therefore the reduction in volume, there will be reduction in volume, but the rate of decrease in volume is decreased. I think when the pressure is increased, say by delta P units, the fluid mass gets compressed, that is the molecules of fluid come close together and the volume of fluid gets decreased, say by delta V units. Instead of dP and dV, I am using delta P and delta V. when the pressure on the fluid is further increased, say by another delta P units, the further decrease in volume of fluid is less than delta V. The reason is, as the molecules already have become close together, with further increase in pressure, the molecules have lesser freedom to come still closer together. Therefore, the molecules which are held close together offer more resistance to further compression with further increase in pressure. Therefore, with increase in pressure, the compressibility of fluid decreases. So, the rate at which the decrease in volume of fluid increases is decreased. I hope you understand the concept. So, with increase in pressure, the compressibility of fluid decreases. The ease with which the gas can be compressed decreases, say with increase in pressure. The reduction in volume decreases with increase in pressure. As the bulk modulus is nothing but the reciprocal of the compressibility of the fluid, so with decrease in compressibility, what happens? With increase in pressure, the bulk modulus of elasticity of the fluid increases. So, with increase in pressure, the compressibility decreases. Therefore, the bulk modulus of elasticity increases, because bulk modulus of elasticity is the reciprocal of the compressibility. For example, if you take water, the bulk modulus of water, it gets roughly doubled as the pressure is increased from 1 atmosphere to 3500 atmosphere. So, the bulk modulus of elasticity of water gets doubled, gets increased as the pressure is increased from 1 atmosphere to 3500 atmospheres. Okay, now let us discuss the parameters affecting the bulk modulus of elasticity of fluid. So, let us take what is the influence of temperature on the bulk modulus of elasticity of fluid. So, if you take gases, now pressure and temperature are related as far as the gases are concerned. When there is an increase in pressure, the temperature increases. When the temperature increases, the pressure increases because of molecular activity. So, when you increase the temperature, the molecular activity increases, the molecules come closer together. So, they are closely packed and therefore, the pressure increases. So, as the temperature increases, pressure also increases, and hence with increase in temperature, what happens? There is an increase in bulk modulus of elasticity, because there is a decrease in compressibility. As the molecules come closer together, with increase in pressure, with increase in temperature, the compressibility reduces and therefore the bulk modulus of elasticity increases. Whereas in case of liquids, with increase in temperature, there is a decrease of bulk modulus of elasticity. Now, ordinarily the liquids are considered incompressible. So, what happens with increase in temperature? The molecular activity increases, the molecules become widely spaced, and therefore the bulk modulus of elasticity may decrease. In most of the problems involving the flow of liquids, the effect of compressibility is neglected because the liquids are generally considered incompressible. So, we talk about compressibility only in case of gases. We do not talk about compressibility of liquids, because in most of the fluid problems in engineering, the effect of compressibility of liquids is neglected because the liquids are generally considered incompressible. So, liquids in general have a very high bulk modulus of elasticity because their compressibility is very less. Is ignored, you can ignore it, or the compressibility is very less, therefore the bulk modulus of elasticity is very high. Therefore, the change in density or volume with increase in pressure is very small, even when the pressure exerted is very large. So, there is no change in the volume or mass density even if you increase the pressure to a very large extent. The change in density or volume is very small in case of liquids. Whereas in case of gases, even for a slight variation in pressure, there is a huge change in the density or volume. Therefore, in most problems involving flow of liquids, they are treated incompressible. So, please note, liquids are incompressible, gases are highly compressible. However, in some special cases where the change in pressure is either very large or sudden, it is necessary to consider the effect of compressibility. For example, say water hammer in case of pipes. We will discuss water hammer when we talk about pipes. So, there we have to consider the elasticity of the fluid, that is the liquids. So, where there is when the change in pressure is either very large or the change in pressure is occurring suddenly, then it is necessary to consider the effect of compressibility of liquids. In problems involving flow of gases, the compressibility of gases needs to be considered definitely. With even a slight change in pressure, they undergo a considerable change in its mass density or volume. Okay. Now, let us work out a numerical problem on compressibility. It is example 10. In continuation of the previous examples, we have solved on the other properties such as viscosity, mass density and specific weight. A fluid compressed in a cylinder has a volume of 0.01132 meter cube at a pressure of 70.3 kgf per centimeter square. What should be the new pressure in order to make its volume 0.01121, that is, the volume gets reduced. So, what should be the increased pressure in order to reduce its volume to 0.01121 meter cube from the original volume of 0.01132 meter cube. You are asked to assume the bulk modulus of elasticity K of the liquid as 7030 kilogram force per centimeter square. So, let us put the data given. Let V1 be the volume of compressed fluid, that is 0.0132 meter cube. It is already in a compressed state. We are increasing the compression. So, when the volume of compressed fluid is so much, the pressure of compressed fluid is given, that is 70.3 kgf per centimeter square. Let that be P1. So, let us convert kilogram force per centimeter square to SI units, that is Newton per meter square. So, kilogram force 1 kgf is 9.81 Newton. So, multiply by 9.81 and then centimeter square should be converted to meter square, that is 10 power minus 4 meter square. 1 centimeter square is equal to 10 power minus 4 meter square, because 1 centimeter is 10 power minus 2 meter. So, 1 centimeter square will be 10 power minus 2 whole square meter square. It is 1 by 100 whole square. So, this becomes this much, 6896,430 Newton per meter square. Let when the pressure is increased from P1 to P2, the new volume is V2. So, V2 is less than V1, P2 is greater than P1. So, we know the formula, bulk modulus of elasticity K is the change in pressure divided by the strain, the volumetric strain, the change in volume divided by original volume. The change in pressure is what? The increase in pressure. The increase in pressure is P2 minus P1. The change in volume, that is decrease in volume, is V1 minus V2, that is 0.01132 meter cube minus 0.01121 meter cube. So, this much you get. Now, original volume of the compressed fluid is this much, that is V1. So, V is V1, dV is V1 minus V2, dP is P2 minus P1. V1 is the original volume, P2 is the new volume after increasing the compression. P2 is the pressure corresponding to P2 is the increased pressure and P1 is the original pressure. So, dP, P2 we do not know, it is asked. P1 is known, V1 minus V2 is dV, V is V1, therefore you get this much, and then you can find out P1, what is P1 from this, or P2 from this, sorry, P2 from this. Because K is known, and this quantity is known, so P2 is the only unknown that can be determined. Now we move into the next property, surface tension and capillarity. I think we will stop at this stage, and we will continue in the next module, the surface tension in the next module. So thank you.